All right, so yesterday we talked about, well, we did 3.3 was all the ways that you can prove lines are parallel. So remember, like all the converses to 3.2. So in 3.2 we said if the lines were parallel, then alternate interior, alternate exterior, and corresponding angles were what? Congruent. And same set interior would have been? Supplementary. Good. And then we flip-flopped it yesterday. And we said if those things are true about the angles, then the lines are parallel. So if the two corresponding angles are congruent, then the lines are parallel. If two alternate interior angles are congruent, lines are parallel. If two alternate exterior are congruent, lines are parallel. And if two same set interior angles are supplementary, then the lines are parallel. So we flip-flopped them all to be the converse. So number 1 says find the value of x that makes P parallel to Q. So in order for those lines to be parallel, what has to be true about those two angles? Nope. They're congruent, right? What's true about the location of this angle and this angle? Alternate interior. So alternate interior have to be congruent, which means 2x plus 43 has to equal 3x. And then subtract the 2x. 43 would equal x. So the value of x that makes those two congruent, which makes the lines parallel, would be 43. Questions on that one? Yep. Say again. So remember we said in order for the lines to be parallel, alternate interior angles are congruent. You see that those are alternate interior angles? So in order for them to be congruent, they'd be equal to each other. You set them equal to each other and then solve for x. So is there enough information here to show that these are parallel? Yes. And what theorem would it be? Alternate interior, opposite sides, right? So it's alternate, and then they're in between the two parallel lines. So this is the alternate interior angles theorem, and what's the most important part of this? Good, converse. Converse is when you're proving the lines are parallel. So if I say theorem says if the lines are parallel, then the alternate interior angles are congruent. This time we want to show that the lines are parallel, so we have to use the converse. Okay, 3 says which of these lines are parallel? So there's two sets. I could either say that these two are parallel, or I could say that these two are parallel. Which two are parallel?
EF and DG.
EF and DG, and why?
Because they're supplementary.
Perfect. So this 95 and this 85 would add together to give me 180. This 80 and this 100 would add up together to give me 180. So these are same side interior if these two are my lines, and then, or the parallel lines, and then ED and FG would be the transversals. So ED is parallel to FG. Nope, other way around. EF is parallel to DG. The other way around doesn't work, right? If I took this 95 and the 80 and added them together, is that 180? No. How about 85 and 100? No. Does that make sense? Why the first pair are parallel and not the second? So if I go this way, like actually rotate it, right? If these were parallel.
It's not an even rectangle.
Well, even if it doesn't, so yes, it's obvious that way, but they're not always going to be drawn to scale, so be careful with that, okay? So when I look at those, if those were parallel, then these two would be same side interior and would have to add up to 180, and they don't. They're 185. Does that make sense? And then same here. These two would have to add up to 180, and they don't. They're 175.
So why would it be ED and FG?
Because we just said that these can't be these can't be congruent. Sorry, those can't be parallel because these are not supplementary. If these are not supplementary, then those lines can't be parallel. You're welcome. Okay, number 4 says in the figure, if HJ is parallel to KL, so this one is parallel to this one, and KL is parallel to MN, what can you conclude?
HJ is parallel to MN.
Good, and how do you know that?
Translated.
of
angles theorem?
of parallel lines. So you're so close. Transitive property of parallel lines. Yes.
Wouldn't the lines be on top if they're representing lines?
If they say that again.
Wouldn't the lines be on top of the HK and the MN? Because
Oh, yeah. Sorry. You would be like this and like this. Yeah. So when you don't have the lines, that's implied that it's a segment, which would have been okay. If you wanted it to be raised, then you would have made sure that you had that symbol. But if you leave it off, I assume you're talking about a segment.
What are the two slashes?
The vertical ones, parallel. Any other questions on the warm-up? I had the passes on the podium. All right, perpendicular lines is chapter 3, section 4. So we're going to do notes, and then I'll go back to the homework from last night. So now we're going to learn a bunch of theorems about perpendicular lines, some definitions, and then some theorems about perpendicular. What's perpendicular? Two lines that intersect at a right angle, right? Everybody good on perpendicular? Yep. Okay, good. So the first thing we're going to learn about is a perpendicular bisector. If you dissect that, perpendicular means right angle, bisector means what? What happens when you bisect something? Cut it in half. So we're putting those two together. We're saying that the perpendicular bisector would be a segment that's a line perpendicular to another segment at its midpoint. So this red line, let's make it an actual line, bisects the blue segment. And it hits it at a right angle, which means that the red line is the perpendicular bisector of the blue segment. So think about what's happening here. Can I say that in reverse? Can I say the blue segment is bisecting the red line? Can you find the midpoint of a line? Kind of a trick question. Think about a line. What's wrong? What do you know about a line? Goes forever. So if you had something that goes forever, could you find the middle of it? No. Does that make sense? So a line can bisect a segment. A segment can bisect a segment. A ray can bisect a segment. But none of those things can bisect a line or a ray because it wouldn't end. God bless you. So when you look at something like this, you'll notice that these are going to be segments, meaning they have endpoints, right? So if I said that this was line M and this, or segment M, and this is line L, this would have another endpoint. So let's say that's MC. I can say that line L is the perpendicular bisector of segment MC. But you cannot say the other way around. One, it doesn't even look like it's the middle of it. But two, you can't bisect a line. There's no midpoint of a line. And then the second bullet says the shortest segment from a point to a line is perpendicular to the line. So if I picked a point here, call this J, and I said, how do I show the distance from point J to segment MC? Okay? You can't just start drawing lines and say that those are all distance, right? Those are all totally different. The true distance from a point to a line is the perpendicular segment that connects them. So the only one that would show true distance and the shortest distance would be a perpendicular segment like that. Okay? So from point to line, or point to segment, or point to ray, the shortest distance would be a perpendicular segment connecting those. Questions on any of that? All right, so example 1 says, name the shortest segment from point A to BC. So we're saying point A to segment BC. What's the shortest segment? AP. Everybody sees that, right? It's kind of obvious this time, but you could even have something that's a little bit closer to it drawn. And you would have to know that that shortest segment is the one that's got the right angle on it. B says write and solve an inequality for x. What's an inequality? It's not equal, so it could be. What are the relationships we use for inequality? Greater than, less than, right? Does that make sense? So if I'm writing and solving an inequality, then I'm going to say that the shortest segment would be this, and one longer than it would be this, which means you can write it two ways. 12 is going to be less than x minus 8. Or you could have said x minus 8 is going to be greater than 12. Those both have the same meaning. With me so far? How do I solve it? Add the 8. And whether you do it on this side or you do it on this side, both of these are read as x is greater than 20. So when you solve inequalities, remember it's exactly the same as if it's an equal sign, except for what? Can you remember where things change when it's an inequality? Yep.
When you divide.
By what?
A negative.
Good.
Yeah.
When you divide or multiply both sides by a negative, your sign flips. Everybody remember that rule? Yeah, so if I had something like negative 2x is greater than 10, when I divide by that negative 2, I have to flip the sign to face the other way. Salvador.
So why exactly would you subtract the 12 and x minus 2?
Why would you subtract the 12? Is that what you said?
I mean, why would you like do the equality?
Why? Say that again. I'm sorry, I can't hear you.
Why would you do an inequality with that?
Well, because we don't know that they're equal. All we know is that 12 has to be shorter than x minus 8, right?
Mm-hmm.
I don't know anything about the actual length of that x minus 8. All I know is it can't be any smaller than 12 because 12 is the one that's perpendicular. So it's got to be the shortest. All right, there's 3 perpendicular theorems in this section, okay? The one that has a name is the middle one. The first one says, if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So think about what this is saying. If you have 2 intersecting lines, like this one and this one, and they form congruent angles, so this one's congruent to this one, how would I know that those are perpendicular? Why is this true? What's true about 2 angles that form a line? Go ahead.
They equal 180.
They add up to 180. That's called a what? No, like what's the angle measurement? Why is it that 2 lines, what do we call that? There's a postulate that says that 2 angles that form a line are supplementary. Do you remember the name of the postulate?
Linear pair.
Good. Linear pair postulate. So the linear pair postulate tells us that those 2 angles are supplementary, right? That add up to 180. Does that make sense? If they're the same, what does that make each of those measurements?
Congruent.
Right? So if they're congruent and they add up to 180, what do they have to be? What's 180 divided by 2?
Corresponding.
90. If they're both 90, what's true about those lines? And if there's right angles there, what's true about the lines? They're perpendicular. So this theorem just took all those little parts we just talked about and put it into one thing. All right, the second one is the one with the name. So perpendicular transversal theorem, okay? Which says in a plane, if a transversal is perpendicular to one of 2 parallel lines, then it's perpendicular to the other. Perpendicular. All right, so let's look at where this one comes from, right? So if I've got these 2 parallel lines, right, it says N is parallel to P, and I've got that N is perpendicular to Q, okay? So before this theorem, think about what we know about these 2 lines. If this angle is a right angle, what's true about where Q meets P? It's also a right angle, and why is that? They're corresponding. If they're corresponding, then they're, and the lines are parallel, then they're congruent, right? So if one's 90, the other one's 90. Does that make sense? And then that means that Q is now perpendicular to P. So this theorem just takes those steps that would literally be that angle is equal to that angle because they're corresponding. This angle equals 90, so then this equals 90. That would be the substitution. And then if they both equal 90, they equal each other. So that you're taking 3 steps and putting it into one with this proof. With this theorem, okay? So that is the perpendicular transversal theorem. If one of the 2 parallel lines is perpendicular to the transversal, then so is the other one. All right, then the last one. If 2 coplanar lines are perpendicular to the same line, then the 2 lines are parallel to each other. So this one now is kind of like the converse of that last one. Now it's saying if they're both perpendicular, then the lines are parallel, okay? And again, think about like why that's reversed.
So when you're supposed to write it down, what theorem do you put like as a...
For the name, you actually have to write it out.
Like so we write down perpendicular transversal.
That one you can use the name. Yeah, so perpendicular transversal theorem, you can either write out that name or you can write what it says.
Oh, so we can write down what it says for the...
For the other 2 that don't have a name, you've got to you can shorthand it a little bit, but yeah, you've got to give me the gist of that. So now this one says, if the 2 lines are perpendicular to the same line, then those 2 lines are parallel. And again, think of where this comes from. If I call this angle 1 and angle 2, if angle 1 equals 90 and angle 2 equals 90, what's true about angle 1 and angle 2? They're congruent. If they both have the same measure, they're congruent. Yes, you with me?
Yes.
And then if angle 1 equals angle 2, what's true about those lines? So if angle 1 equals angle 2, what do you know about line R and line S?
They're parallel.
They're parallel. Why is that?
Because the line is
The corresponding.
Because of the corresponding angles. So the actual wording would be the corresponding angles postulate converse, right? We said if they're corresponding, so then the lines are parallel.
What is the converse?
That's the converse. If we're proving the lines are parallel, it's the converse.
So why is it possible?
Postulate, it's the postulate converse. So the postulate is what says that if the lines are parallel, then corresponding angles are congruent. The corresponding angles postulate converse says if the 2 angles are congruent, then the lines are parallel. So this actually takes those 2 things and again puts it together. If 2 coplanar lines are perpendicular to the same line, then the 2 lines are parallel. So it kind of takes a couple of those steps and puts it together. So if you're given a proof, let's say it's open-ended, you can choose either way to work it out. You could go the long route if that's what you're comfortable with, or if you wanted to wrap it up with just this one theorem, you could do that too.
So what would the name of their theorem?
There is no name, which means you're going to write out 2 lines perpendicular to the same line, then those lines are parallel, something like that.
Do we have to memorize that for the test?
Yeah,
Could we just name it the perpendicular?
it doesn't have a name.
What's the converse of
No, because that doesn't have an initial one. It's kind of like the perpendicular theorem converse, but it doesn't have its name. You should invent the name. We just looked at, we said if 2 intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. No. All right.
The perpendicular coplanar theorem.
You're just making stuff up. All right, example 2 says, write a 2-column proof to prove that R is perpendicular to T. So we're going to do this together. Label what they gave you. So R is parallel to S, means that this line is parallel to this line. So really ugly arrows, but you get the point. Okay? And angle 1 equals angle 2. So how would we prove, without actually going through the whole process, how would we prove that R is parallel to T? Perpendicular to T. Yep, go ahead.
Angle 1 and angle 2 are corresponding. No, congruent.
angle 1 and angle 2 are congruent, but in order to get that this and this are perpendicular, what would we have to say about 1 and 3, let's say? You'd have to prove that 1 and 3 are congruent because two angles, right, that form a line that are congruent would form perpendicular lines. Does everybody understand that? So that we eventually have to get to that this one would equal this one. That's the only way we're going to get that they are both 90. Because if they're a linear pair, they add up to 180. And if they're equal, that means they're each 90. Does that make sense? Okay, so now let's think about how we could write that out. So the first thing I would write out is what? The given. So R is parallel to S, and angle 1 is congruent to angle 2. I'm going to say that's given. Okay, so then what we know now is that if those lines are parallel, what can we determine? What did we say about 2 and 3? They're corresponding. So if the lines are parallel, what's true about corresponding angles? They're congruent. So angle 2 would be congruent to angle 3. And that's the corresponding angles postulate. Now 1 is equal to 2 and 2 is equal to 3, which tells you what?
That 1 is equal to 3.
1 is equal to 3, and what is that? Good. You can just give me transitive property, but I wrote transitive property of equality. So now I've got that these are now congruent. And if we go back to the theorem, so do we have two angles that are linear pairs that are congruent? Yep, so I can go to the prove, which is R is perpendicular to T. And I can say two angles that are a linear pair and congruent form perpendicular lines. All right, this one. Oh, yeah. Write a two-column proof. So given angle EHF, okay, is congruent to HFG. So those are the ones that are marked here. EHF and HFG. Given those two are congruent and this is perpendicular, prove that EH is also perpendicular to GH. So what did we say, if you go back to the slide with the theorems, how can I prove that a line is perpendicular to another line? Using what we talked about today. Which says if one of two parallel lines, right, is perpendicular to one line, then it's perpendicular to the other. So what I have to do is prove that EH is parallel to FG. And if that's the case, then I can say EH is perpendicular to HG because FG is perpendicular to HG. So I'll kind of help you with these steps because, again, it's a little bit complicated when you don't have anything given to you. But I'll start with the given.
On the quiz, is it going to have us solve the entire problem?
I actually haven't seen it yet. So I'll be able to answer that for you on Monday. I don't think he's made it yet.
What's the quiz again?
Wednesday. Should be on your to-do list. All right, so number 2, let's say, okay, if those two angles, if this angle and this angle are congruent, what do I know about EH and FG?
They're perpendicular.
Not perpendicular, right? EH and FG.
Parallel.
They're parallel. How do I know that? What are the ways to prove lines are parallel?
They'll never intersect.
But how do you prove it? Remember, there's 4 ways. Now there's 5 ways. Either alternate interior angles are congruent, corresponding angles are congruent, alternate exterior are congruent, or same set interior.
Alternate interior.
We've got alternate interior. Everybody see that? Those 2 blue arcs are alternate interior. So this is the alternate interior angles theorem converse, because we're proving that the lines are parallel. So now I know these are parallel. And if one of 2 coplanar lines that are parallel is perpendicular to a third line, or the transversal, then the other line, which in this case is EH, would also be perpendicular to HG. So that's the perpendicular, oops, daisy. Transversal theorem. This will be on the video. This is what was due this morning. From what I understand, you guys struggled with 9. There's a lot of words in it. Words scare people. Okay? That's a sample answer of how you can answer it. It's not the only answer. On Monday, remind me and we'll go back over this again. So Monday we get to review 3, and 3-4. And then same thing for Tuesday, really. Tuesday we'll review all 3 sections. And then Wednesday will be your quiz on these 2 sections.